In February of 2025, a researcher in Kansas sat down at his desk, opened a folder of images from the most powerful telescope ever built, and counted galaxies. He counted them by hand, 263 of them, each one a spiral, photographed by the James Webb Space Telescope, taken from a region of the sky called the Advanced Deep Extragalactic Survey Field, a patch of darkness that, before Webb opened its eye, had appeared empty. Now, with the telescope's gold mirror feeding in light from the deep universe, that same patch of darkness was revealed to be full of galaxies, full of structure, full of light from the early cosmos, light that had been traveling for billions of years before reaching the lens of the most expensive scientific instrument humanity has ever built. The researcher's name was Lior Shamir. He was a computer scientist, not an astronomer, and what he was doing was very simple. He was looking at which way they spun. A spiral galaxy, when you photograph it from above, has a direction of rotation. The arms curl one way or the other, like water swirling down a drain, clockwise or counterclockwise, depending on which side you were looking from. And astronomers for decades had assumed that in a sufficiently large sample of galaxies, taken from a sufficiently random patch of the sky, the count of clockwise spinners and counterclockwise spinners should be approximately equal, about 50-50. Some random scatter, but no systematic preference. This is, after all, what a homogeneous, isotropic universe is supposed to do. A universe with no preferred direction. A universe that looks the same in every direction you point your telescope. That is the universe described in every cosmology textbook. That is the universe predicted by the standard model of cosmology, the one that has dominated the field since the late 1990s. A universe with no axis. A universe that, on the largest scales, has no inside and no outside, no left and no right, no up and no down, and certainly no spin. So, Shamir counted, and the count was wrong. About 2/3 of the galaxies were rotating in one direction. About 1/3 were rotating in the other. The split was not 50-50. It was not random. It was not within any reasonable margin of statistical fluctuation. The probability of obtaining such a skewed distribution by chance, given the assumption of an isotropic universe, was less than 1 in 1,000. The galaxies were not random. The galaxies had a preferred direction. When Shamir published the result in March of 2025, in the monthly notices of the Royal Astronomical Society, the response from the cosmology community was uncomfortable. Some of his colleagues argued that the asymmetry was an artifact, a measurement bias caused by the rotation of the Milky Way itself. Others suggested that, with only 263 galaxies, the sample was too small to draw firm conclusions. Most agreed that the result needed to be confirmed with larger surveys, with different telescopes, with independent analyses. But there was a second, much stranger possibility. A possibility that Shamir himself raised in his paper. A possibility that, if it turned out to be true, would force a reconsideration of nearly everything we have ever assumed about the cosmos. The possibility was this: maybe the universe is rotating. Not the galaxies inside the universe itself, the whole thing, spinning. And if the universe is spinning, then the asymmetry that Shamir found in the JWST images is not a measurement bias and not a statistical fluke. It is a hint. It is the faint, almost invisible fingerprint left by an act of rotation that began before the first atom condensed out of the cooling fire of the Big Bang. An act of rotation that the universe itself inherited from something older, something that came before. And the only physical model in modern theoretical physics that seriously proposes a parent for our universe, a structure from which the cosmos could be born already spinning, is a model that has, until recently, sat at the fringes of cosmology, treated as speculation, almost as a curiosity. Black hole cosmology, the hypothesis that our entire universe is the interior of a black hole, that what we call space, the vast and apparently boundless arena in which all the galaxies and stars and planets and atoms exist is the inside view of a singularity that, from the outside, sits at the center of some other, larger universe, and that the spin we see in our cosmos, the spin of every galaxy, every solar system, every atom, is not native to our reality. It is inherited. It is the slow, residual angular momentum of the parent black hole, transmitted across the boundary of birth into the matter and structure of everything we will ever observe. If this is true, then everything that spins for one reason. It is remembering. I want you to hold that idea in your head for a moment. Not because we are going to assume it is correct. We are not. The black hole cosmology hypothesis is, even today, a minority position in theoretical physics. The JWST asymmetry may yet turn out to be measurement bias. The universe, as far as anyone can prove, may not actually be rotating at all. But the question that the asymmetry has put on the table, the question of why anything in the cosmos spins, of where the angular momentum of the universe comes from, of how a cloud of gas at the moment of the Big Bang turned into a cosmos in which nothing is still, is one of the deepest unsolved problems in modern physics. It is older than relativity. It is older than the discovery of galaxies. It is older than the telescope. And the answers we have are only partial. They are good enough in some cases to tell us how a star spins. They are not good enough to tell us where the spin came from in the first place. They are not good enough to tell us why the universe contains rotation at all instead of containing matter at rest. This is the question we are going to spend the next 2 hours unraveling. Why does everything in the universe spin? The Earth spins. Once every 24 hours, on an axis tilted 23.5 degrees from the plane of its orbit. It spins so steadily, and has spun so steadily for 4.5 billion years, that we measure time itself by its rotation. The day is a unit of spin. The Earth is not unusual. The sun spins once every 25 days at the equator, more slowly toward the poles. Every planet in our solar system spins. Even Venus spins, although so slowly and in the wrong direction that a single Venusian day is longer than a Venusian year. Mercury, the planet closest to the sun, where the gravitational tides are strongest, spins so reluctantly that its rotation is locked to its orbit by an exact 3:2 ratio. But it spins. Stars spin, galaxies spin, galactic clusters rotate, although slowly. Asteroids tumble through space, every one of them turning end over end as they orbit the sun. Comets rotate as they fall in toward perihelion. Black holes, the densest, most compact, most extreme objects in the cosmos, spin so fast that their event horizons drag the very fabric of space around with them, an effect called frame dragging that has been measured directly in our own galaxy. Subatomic particles spin, or rather, they have a property called spin, which is not exactly the same as macroscopic rotation, but which behaves in many of its mathematical features as if it were. Every electron in your body has a spin. Every proton, every neutron, every photon of light streaming from your screen into your eyes carries spin. The fundamental particles of nature are not still. They have, baked into them at the deepest level of the Standard Model, a property of intrinsic rotation. Across every scale of the universe, from the largest superclusters of galaxies down to the smallest leptons in the quantum foam, things are not at rest. They are turning. Why? This is not a rhetorical question. It is, in physics, an extraordinarily hard one. And the answers, the partial, incomplete answers we have begun to assemble across 2 centuries of observation and theory, point in surprising directions. They point toward conservation laws that govern the behavior of matter at every scale. They point toward the early conditions of the universe, in the first fractions of a second after the Big Bang, when fluctuations in the density of the primordial plasma seeded what would become every rotating structure we now see. They point toward the geometry of space-time itself, which carries within its tensor equations a deep relationship between mass, motion, and the curl of inertial frames. And they point ultimately toward a conclusion that will probably make you uncomfortable. The conclusion is this: we do not know, we have models, we have approximations. We have detailed, mathematically rigorous descriptions of how angular momentum is conserved and transferred between objects in known systems. We can predict, with extraordinary precision, the rotation rate of a neutron star formed from the collapse of a massive star whose initial spin parameters we already know. We can predict the orbital periods of planets, the precession of gyroscopes, the wobble of a top, the eddies of a fluid in motion. But the deeper question, the question of where the angular momentum came from, of why the universe is full of rotation rather than empty of it, of why our cosmos contains spin instead of stillness, that question has no settled answer. And it is the question we are going to try in the next 2 hours to look at directly, without flinching, across every scale at which the question presents itself. We are going to start at the largest scale, the scale of the universe itself, and we are going to descend. Galaxies, solar systems, stars, planets, moons, asteroids, then deeper, atoms, nuclei, protons, quarks. The intrinsic spin of fundamental particles, the strange quantum property that has nothing to do with rotation as we know it, and yet behaves in many ways exactly like rotation. And at the bottom of that descent, we are going to find ourselves back where we started, at the level of the universe, asking the question that Leor Shamir's 263 galaxies put back on the table. Is the universe spinning? Did it always spin? Was it born already turning? You are sitting somewhere right now, probably at a desk, or in a bed, or on a sofa, or in a vehicle of some kind. You feel still. You feel as though you are not moving. The cup of water on the table beside you is not visibly trembling. Your hands rest motionless on whatever surface they are resting on, but you are not still. The earth beneath you is rotating on its axis at approximately 1,700 kilometers per hour at the equator. If you are reading this from any point not at the geographic North or South Pole, you are being carried sideways, right now, at speeds that approach the cruising velocity of a passenger jet. That is only the first layer of motion. The Earth, while spinning on its axis, is also orbiting the Sun. Its orbital velocity is approximately 107,000 kilometers per hour. That is faster than any spacecraft humans have ever sent to deep space, with the exception of the Parker Solar Probe at perihelion. As you sit here, motionless, you are being hurled around the Sun at a velocity that would, if it were applied to you in any direction relative to the ground beneath you, kill you instantly. That is also only one layer. The Sun, while you are orbiting it, is itself orbiting the center of the Milky Way galaxy. The Sun's orbital velocity around the galactic center is approximately 828,000 kilometers per hour. You are being carried along with it. Your motion through the galaxy, as the galaxy itself rotates, is at nearly 1,000,000 kilometers per hour, and the orbit takes about 225 million years to complete. The last time the Sun was at this point in its galactic orbit, dinosaurs had not yet evolved. That is still only one more layer. The Milky Way itself is moving. It is part of a small group of galaxies called the Local Group, which is being pulled by the gravitational influence of larger structures, the Virgo Cluster, the Great Attractor, the Shapley Supercluster, at a velocity of approximately 2 million kilometers per hour through the cosmic background. You, sitting where you are, feeling still, are moving through space at velocities your body has no way to perceive. You are spinning, you are orbiting, you are being carried along in a cosmic current. You are, in every meaningful sense of the word, in motion. The stillness you feel is a lie. It is the most basic, most universal lie that your senses tell you. The lie of rest. The lie that the universe in which you live is the kind of place where things can be motionless. Nothing in the universe is motionless. Nothing has ever been motionless. The very atoms that compose your body in the moments between motions of muscle and breath are vibrating in their lattices, jittering against their neighbors, and at the most fundamental level, the level of their constituent quantum fields. Those atoms are also spinning. This is the deep, almost metaphysical reality of the cosmos we live in. There is no rest. There is no stillness. There is only motion, layered on top of motion, layered on top of motion, all the way down. And nearly all of that motion is rotation. Before we can ask where the rotation of the universe came from, we have to understand the law that governs all rotation, because that law is the one constraint that connects every spinning thing in the cosmos, from a child's top to a galaxy. Every object that turns is bound by it. Every object that ever turned, ever, in the entire history of the universe, has obeyed it. The law is called the conservation of angular momentum. You have almost certainly seen it in action, even if you have never thought of it that way. Consider a figure skater. She is spinning slowly on the ice, with her arms extended outward. The audience watches as she begins her routine, her arms held wide, her feet drawing a slow circle on the ice. She is rotating, but unhurriedly. The pace is graceful, deliberate. Then she pulls her arms in. The moment her hands cross her chest, the moment her arms tuck close to her body, the speed of her rotation jumps. She accelerates, suddenly, dramatically, from a slow turn into a near blur. The ice beneath her begins to hum with the speed. She is not pushed off the ice. She has not added any new energy to her motion. She has simply changed her shape, drawn the mass of her arms closer to the axis around which she is spinning, and the universe has rewarded her with a faster rotation. This is conservation of angular momentum. It says that for any rotating system, in the absence of external forces acting to change its rotation, the product of the system's moment of inertia and its angular velocity is constant. In simpler terms, if you compress a spinning thing, if you bring its mass closer to its axis of rotation, it must spin faster. There is no way around this. It is not a tendency or a preference. It is a law, as binding as the conservation of energy. And this law has consequences, because every collapsing thing in the universe, every cloud of gas drawing inward under its own gravity, every cluster of dust assembling into a star, every supernova remnant compressing into a neutron star, every primordial fluctuation curling itself into a galaxy, is a system that begins large and ends small. Every such system, if it contains any rotation at all when it begins, will rotate faster as it shrinks. And here is the catch. It is essentially impossible in the early universe for any such system to begin with zero rotation. There is always some amount, however small, some random walk of velocities, some statistical fluctuation in the angular momentum of the primordial gas, some torque imparted by neighboring overdensities pulling on each other in slightly different directions. The cosmos, at the moment of structure formation, was not perfectly smooth. It was textured, and the texture meant that as gas began to collapse into the seeds of galaxies and stars, there was always some net rotation present in the collapsing material. A small rotation multiplied by an enormous compression becomes a fast rotation. This is why everything in the universe spins, or, more precisely, this is why everything that has ever collapsed spins. The rotation does not have to be created. It has to merely exist at any non-zero level before the collapse begins. And because perfect zero is essentially impossible to achieve in any realistic distribution of matter, every collapsing system in the cosmos ends up with detectable spin. The figure skater, the collapsing cloud, the forming star, the aggregating planet, the supernova remnant, the merging black hole, all of them, every one, pulled their mass inward and accelerated their spin in obedience to the same law. The same law that governs the skater on the ice governs the formation of galaxies in the early universe. The same conservation principle that turns a slow pirouette into a blur turns a leisurely cloud of gas into a relativistic neutron star. It is, in some sense, the most universal law of motion that exists. It applies at every scale. It is symmetric across time. It is built into the deepest mathematical structure of physics, deriving, through a theorem proved by the German mathematician Emmy Noether in 1915, from the rotational symmetry of space itself, the fact that empty space looks the same in every direction, the fact that there is no preferred direction in the void. This single fact, mathematically, generates the conservation of angular momentum. If you live in a universe whose vacuum is rotationally symmetric, and we appear locally to live in such a universe, then any rotating thing will continue to rotate, and anything whose moment of inertia decreases will rotate faster. There is no way out. There is no escape. Once a system has angular momentum, it has angular momentum forever, until something external takes it away. This is why every star in the night sky is spinning. The clouds of hydrogen gas from which stars condense are vast, typically several light years across, sometimes hundreds of light years. They are cold by stellar standards, with temperatures in the range of 10 or 20 Kelvin. They are tenuous, with densities of perhaps a few hundred molecules per cubic centimeter. And they are, almost without exception, slowly turning. The galaxy itself is rotating, pulling the gas along in its great spiral arms. And as the gas drifts through the galaxy, it picks up shears and torques that imprint a slow net rotation on every cubic parsec of interstellar medium. When such a cloud begins to collapse, when some triggering event, perhaps the shock wave of a nearby supernova, compresses a region of gas past the threshold of gravitational instability, the collapse is not symmetric. The gas falls inward, faster and faster, but the small initial rotation does not vanish. It is conserved. As the cloud shrinks from light years across to mere astronomical units, the rotation rate climbs from 1 full turn per 100 million years to 1 full turn per day, then per hour, then per minute. By the time the central density is high enough to ignite hydrogen fusion, by the time the protostar at the center of the collapse has become a real star, its rotation rate has been amplified by a factor of trillions. The gentle galactic shear that imprinted the original spin on the cloud has been concentrated by the inexorable arithmetic of conservation of angular momentum into a fast-rotating young star whose surface velocity may approach a sizable fraction of the local escape velocity. This is why young stars spin so fast. The Sun, in its earliest years, may have completed a full rotation every few days. Today, 4.5 billion years later, after eons of magnetic braking through the slow loss of angular momentum to the solar wind, the Sun has slowed to its present rotation period of about 25 days at the equator. But in its youth, it was a much faster spinner. And neutron stars, the collapsed remnants of massive stars, can take this principle to its absolute logical extreme. A neutron star is what remains when a star much more massive than the Sun reaches the end of its nuclear fuel and collapses under its own gravity. The core, which had been a ball of iron about the size of the Earth, is compressed in less than a second to a sphere about 20 kilometers across. The change in moment of inertia is staggering. By conservation of angular momentum, the rotation rate of the collapsing core must increase by a factor proportional to the inverse square of the radius. An Earth-sized core that spun once per month, when compressed to 20 kilometers, must spin many hundreds of times per second. This is exactly what we observe. Pulsars, The rapidly rotating neutron stars, whose lighthouse beams of radio emission sweep across the Earth at fixed intervals, are direct evidence of the conservation of angular momentum operating across the most extreme stellar event in the universe. The Crab pulsar, formed from a supernova observed by Chinese astronomers in 1054 CE, rotates 30 times per second. The fastest known pulsars rotate over 700 times per second, their surfaces moving at fractions approaching the speed of light, their compact bodies held together against the centrifugal tear only by the unimaginable strength of degenerate neutron matter. Every one of those rotations is a survival. The original rotation of the progenitor star, slow and gentle, has been amplified across the collapse into a frenzy of motion that ends only when the neutron star itself dies, by accreting from a binary companion, or by colliding with another compact object, or by the slow trickle of magnetic dipole radiation that, over hundreds of millions of years, finally bleeds the rotation away. But the rotation does not die because of external suppression in the early universe. It dies, eventually, only because of the slow leak of energy that any rotating object experiences when it interacts with electromagnetic or gravitational fields. The default state of a rotating compact remnant in deep interstellar space is to keep rotating forever. Until something external removes the angular momentum, take a moment, sit with what we have just said. There is no rest in the universe, not because the laws of physics forbid it, but because the laws of physics actively reward motion, because angular momentum, once present, is conserved, because the universe was born with motion already in it, random, distributed, present at every scale, and because that initial motion has been preserved, concentrated, amplified, transferred from object to object, for the entire 13.8 billion years of cosmic history. Every rotating thing you see because angular momentum was conserved. The galaxies overhead, on the clearest night you have ever known, are all spinning. The Milky Way is spinning. The Andromeda Galaxy, 2.5 million light-years away, is spinning, and is pulling its nearby companions, the small spiral M33 and the elliptical M32, into the same slow rotation. The local group itself, the gravitationally bound cluster of dozens of small galaxies that contains the Milky Way and Andromeda, is in a slow tumble around its mutual barycenter. The local group is part of the Virgo supercluster, which is itself part of the larger Laniakea supercluster, the great cosmic basin that funnels matter inward across more than 500 million light-years of space. All of these structures are turning, some of them very slowly. The rotation period of Laniakea is so long that no rotation has been completed since the Big Bang. The supercluster has spun, perhaps, a fraction of a turn since the cosmos began. But the rotation is there. It is detectable. It exists. And below the level of the supercluster, the rotations get faster. Galaxies with rotation periods of hundreds of millions of years. Stellar systems within galaxies with orbital periods of tens or hundreds of years. The planets of the solar system with orbital periods of months to centuries. The rotations of those planets on their axes with periods of hours or days. The rotations of moons, the tumblings of asteroids, the slow spins of gas giants, and the breakneck pulses of neutron stars, and the impossible whirlwinds at the cores of black holes. The universe is layered. It is a hierarchy of rotations, each one nested inside the next. Each one a consequence of the original angular momentum imprinted at some moment of structure formation, conserved and concentrated through every stage of collapse, surviving across cosmic time. You, sitting where you were sitting, are sitting at the bottom of that hierarchy. You are inside the rotation of the Earth, inside the rotation of the Sun's planetary system, inside the rotation of the galaxy, inside the slow turn of the local cosmic neighborhood. Your motion is the sum of all of those rotations, layered together. Your stillness, as we said before, is a lie. You are spinning. Let us go to the place where the rotation we feel most directly was made, to the moment, 4.5 billion years ago, when the sun and its planets were not yet stars and worlds, but rather a slowly contracting cloud of gas and dust adrift in a quiet corner of the Milky Way. The cloud was not unusual. It was, as far as we can reconstruct, a typical region of the interstellar medium, about 1 or 2 light-years across in its initial diffuse state. Composed mostly of hydrogen, with about 1/4 helium by mass, and a sprinkling of heavier elements, carbon, oxygen, silicon, iron, that had been forged in earlier generations of stars and dispersed by previous supernovae into the surrounding gas. The temperature was around 10 Kelvin. The density was a few hundred molecules per cubic centimeter, almost a perfect vacuum by terrestrial standards, but nonetheless a region of greater than average density compared to the bulk of the interstellar medium around it. And it was rotating, very, very slowly, perhaps once every 100 million years. Then something happened. We do not know exactly what. The leading hypothesis, supported by measurements of certain isotopes in ancient meteorites, is that a nearby supernova, possibly within 20 or 30 light-years, sent a shockwave through the cloud. The shockwave compressed the gas. It pushed the density past the threshold at which gravity could overcome the internal pressure of the cloud, and the cloud began to collapse. Once the collapse had begun, conservation of angular momentum took over. The cloud, which had been turning leisurely once every 100 million years, began to spin faster as it shrank. The original light-year-wide configuration was reduced over the course of a few 100,000 years to something like 1/100th of its initial size, a structure perhaps 100 astronomical units across. The rotation rate, by the inexorable arithmetic of the conservation law, had increased by a factor of 10,000. The cloud was now turning once every 10,000 years instead of once every 100 million. And it was no longer a cloud. It was a disk. This is a crucial point, and it tells you something about why the solar system has the shape it has. As the rotating cloud collapsed, the rotation imposed an axial preference on the geometry of the contraction. Material falling along the rotation axis encountered no centrifugal resistance. It could fall freely toward the center. Material falling perpendicular to the rotation axis, on the other hand, was supported by its own angular momentum. As it tried to spiral inward, it was held back by the same conservation law that had been amplifying its rotation. The result was that the cloud did not collapse evenly. It collapsed faster along its rotation axis than perpendicular to it. The original sphere flattened into a pancake. By the time most of the mass had assembled into the central regions, the leftover material, the gas and dust that had not yet fallen all the way in, formed a flat disk surrounding the protostar at the center. This is why the solar system is flat. This is why all 8 planets orbit the sun in roughly the same plane. Not because anyone designed it that way, not because there is anything special about that particular orientation, but because the original cloud from which the solar system formed had a single net rotation axis, and that axis dictated the geometry of every subsequent collapse and condensation. The disk was where the planets formed. The dust and gas in the disk, slowly cooling, slowly coagulating, eventually clumped into planetesimals, small bodies of perhaps a kilometer across, which then collided and merged into protoplanets, which then grew through further accretion into the planets we know today. Each of these forming bodies inherited the rotation of the disk. Each of them ended up orbiting the sun in the same direction the disk had been spinning. Each of them ended up rotating individually in approximately the same direction. Because the local angular momentum in any patch of the disk was, on average, aligned with the rotation of the disk as a whole. This is why most of the planets in the solar system spin in the same direction. why most of their moons orbit them in the same direction, why the entire solar system, when seen from above the sun's north pole, presents a coherent picture of rotation. Everything orbiting counterclockwise, everything spinning counterclockwise, everything obeying the same axis that was imprinted on the original cloud 4.5 billion years ago. Almost everything. There are exceptions. And the exceptions are interesting because they tell us something about the violence of the early solar system. Venus rotates in the wrong direction. It is the only large planet in the solar system whose axis of rotation is essentially upside down with respect to the rest. Where Earth and Mars and Jupiter and the others spin counterclockwise as seen from above the orbital plane, Venus spins clockwise, slowly. So slowly that a single rotation takes 243 Earth days, which is longer than its own orbital period of 225 days. A day on Venus is longer than a year on Venus. How did this happen? We do not know for certain. There are competing theories. One is that Venus suffered a colossal impact early in its history, a collision with another protoplanet that essentially knocked it over and reversed its rotation. Another is that the dense atmosphere of Venus, combined with tidal interactions with the Sun, gradually slowed and eventually reversed its original spin. A third proposes that Venus has actually been flipped, its mantle and atmosphere having been rotated by complex thermal tidal effects until what was once the northern hemisphere is now the southern. Whatever the explanation, Venus is a reminder that the conservation of angular momentum is a local law. It applies to any closed system, but the planets are not perfectly closed systems. They interact with each other. They interact with the Sun. They interact in the early solar system with a host of other protoplanets and planetesimals, many of which ended their existences in collisions that reshaped the worlds they struck. Uranus is another oddity. Where most of the planets have rotation axes that are tilted only slightly from the perpendicular of the orbital plane, Uranus is tipped over almost 98 degrees. It is quite literally lying on its side. As Uranus orbits the Sun, its rotation axis points first toward the Sun, then perpendicular, then away, then perpendicular again. In an 84-year cycle of seasonal extremity, unlike anything else in the solar system, the Uranian poles experience 42 years of constant daylight, followed by 42 years of unbroken night. Like Venus, Uranus probably owes its strange axial tilt to a violent collision in the early solar system. A large protoplanet, perhaps as massive as the Earth, may have struck Uranus during the chaotic period of planetary formation and tipped it over. The impact would have transferred enormous angular momentum from the impactor to Uranus, redistributing the planet's rotation axis in a way that has never been corrected. These are the wild cases, the exceptions. They are, in some sense, the most informative cases, because they show us what the universe looks like when conservation of angular momentum is interrupted by external interventions. They show us that the orderly rotations we see today are not inevitable. They are the survivors of a much more chaotic period when rotations were being created, destroyed, and reshaped on timescales of millions of years. The moon spins. It rotates on its axis once every 27.3 days, exactly the same period in which it orbits the Earth. This synchronization is not a coincidence. It is the result of tidal locking, a process by which gravitational interactions over long time scales gradually synchronize the rotation of a smaller body to its orbital period around a larger body. The mechanism is straightforward in principle. The Earth pulls on the near side of the Moon more strongly than on the far side. This differential pull stretches the Moon slightly along the Earth-Moon axis, creating tidal bulges on both sides. Because the Moon was originally rotating faster than its orbital period, these bulges did not point exactly at the Earth. They were carried slightly forward by the Moon's faster rotation. The off-axis bulges then experienced a gravitational torque from the Earth, slowing the Moon's rotation. Over hundreds of millions of years, This torque dragged the moon's rotation rate down until it matched its orbital period exactly. From that moment forward, the bulges pointed precisely at the Earth, the torque vanished, and the synchronization became permanent. This is why we always see the same face of the moon. It is not that the moon does not rotate. It does, but it rotates exactly in step with its orbit. From our perspective on Earth, this means we always see the same hemisphere, the one that became, by the slow logic of tidal forces, the moon's near side. The far side of the moon was completely unknown to humans until 1959, when the Soviet Luna 3 spacecraft photographed it for the first time. Even now, no human has ever looked at the far side of the moon with their own eyes. Only spacecraft instruments and the astronauts of Apollo, who saw it from lunar orbit, but never from the ground. Tidal locking is not unique to the moon. It is, in fact, very common. Most of the major moons of Jupiter and Saturn are tidally locked to their parent planets. So, is Pluto's largest moon Charon? And, in an unusual twist, Pluto is also tidally locked to Charon, so the two bodies always present the same faces to each other. They are a doubly locked system. Mercury, the innermost planet, is in a complex resonance with the Sun, rotating 3 times for every 2 orbits it completes, a state that emerged from billions of years of tidal evolution. Across the solar system, in fact, the slow grind of tidal forces is gradually changing the rotation rates of every world. The Earth itself is slowing down. Every century, the day gets longer by a few milliseconds. The energy that the Earth loses through this slowdown is transferred to the moon, which is slowly receding from us at about 3.5 centimeters per year. Eventually, billions of years from now, the Earth will become tidally locked to the moon, and a single Earth day will be equal to a single Earth-Moon orbital period of perhaps 50 present-day days. This will not happen before the Sun engulfs the Earth in its red giant phase. But the trend is real, and it points to the same underlying truth. The rotation of every body in the solar system is slowly evolving, slowly being reshaped, slowly being transferred between objects in obedience to the same conservation law that started the rotations in the first place. Let me linger here a little longer, because there is something profoundly strange about how rotations propagate through a forming planetary system that I want you to feel directly. When the protoplanetary disk around the young sun was still active, when planetesimals were colliding, when protoplanets were sweeping up dust, when the entire arrangement was a violent and chaotic place, the rotation of every body in that system was being constantly renegotiated. Each collision transferred angular momentum. Each gravitational encounter altered an orbit. Each accretion event added to the spin of the growing world. The rotations we see today, on the planets we know, are the residues of millions of years of these violent exchanges. Take Earth. Our planet rotates once every 24 hours, but it did not always rotate at this rate. In its earliest moments, immediately after the giant impact that formed the moon, an event in which a Mars-sized body called Theia struck the proto-Earth with such violence that the merged body emerged molten and the ejected debris condensed into our satellite. The day on Earth was perhaps 4 or 5 hours long. The newly formed Earth-Moon system was spinning at a rate that no physical observer could have stood on it. The surface gravity, in some calculations, was barely sufficient to retain the molten material against the centrifugal force of the spin. Over the following 4.5 billion years, that day has lengthened. Tidal interactions with the moon have transferred angular momentum from Earth's spin to the moon's orbit, gradually slowing our rotation while pushing the moon further away. Geologists who study tidal rhythmites, sedimentary layers laid down by ancient tides, can trace the slow extension of Earth's day across geological time. 600 million years ago, the day was about 21 hours long. A billion years ago, perhaps 18. 2 billion years ago, perhaps 15. The lengthening continues today, at a rate of about 1.5 milliseconds per century. and it will continue for billions of years until the system either reaches a stable equilibrium or is disrupted by the death of the sun. Every clock you own, every measurement of time you make, is calibrated against a rotation rate that is slowly changing. The day is not a fixed unit. It is a slowly relaxing parameter of an evolving rotational system. The fact that we have organized our entire civilization around the cycle of solar light and dark, and that this cycle has been slightly different in every era of Earth's history, is one of the more humbling realizations that the science of celestial mechanics has produced. Jupiter, the largest planet in our solar system, rotates faster than any other planet. A single Jovian day is just under 10 hours long. Despite being 11 times the diameter of Earth and 318 times its mass, Jupiter completes a full rotation in less than half the time it takes Earth to do the same. This is, in part, a consequence of Jupiter's formation. Jupiter coalesced from a much larger volume of the early solar nebula than the inner planets did, and it accreted that material at a stage when the rotation of the disk was still well organized and well aligned. The angular momentum imparted to Jupiter during its formation was correspondingly larger in absolute terms than the angular momentum imparted to Earth or Mars or Venus. But the result of that fast rotation is dramatic. Jupiter's atmosphere, viewed from any reasonable vantage point in space, is a banded chaos of streaming winds and storms. The famous bands of light and dark that any modest telescope can resolve. Those bands are caused by Jupiter's rotation. The rapid spin organizes the planet's atmosphere into latitudinal jets, alternating bands of east-flowing and west-flowing wind, separated by zones of vertical convection that lift bright ammonia clouds upward and reveal darker layers below. The Great Red Spot, a single immense storm that has been observed continuously since at least the 17th century, is a hurricane-like system embedded in this banded flow, its longevity made possible by the steady supply of angular momentum from the planet's rotation. Saturn rotates almost as fast as Jupiter. Its day is about 10.5 hours long, and shows the same banded structure, with its own variants of storms and atmospheric features. Both planets are oblate, meaning they are not perfectly spherical. Their fast rotation flattens them slightly, with the equatorial diameter being noticeably larger than the polar diameter. For Saturn, the difference is dramatic. The planet bulges so visibly at the equator that the oblateness can be seen in any telescopic image. The rings of Saturn, those most famous structures of the outer solar system, are themselves a consequence of rotation. Each ring particle, there are trillions of them, ranging from grains of dust to chunks of ice the size of houses, orbit Saturn in the planet's equatorial plane. The rings are flat for the same reason the solar system as a whole is flat. Angular momentum forces collapsing structures to organize themselves perpendicular to their rotation axis. The rings are a miniature version of the original protoplanetary disk, frozen in time, still illustrating the geometric consequences of rotation that produced our entire solar system long ago. Some of the most extreme rotational behaviors in the solar system, however, are found among the smaller bodies. Asteroids tumble, comets spin, the smallest moons of the giant planets frequently rotate chaotically, their motion influenced not only by the gravity of their parent planet, but by the gravitational tugs of nearby siblings. The asteroid Bennu, recently visited by NASA's OSIRIS-REx mission, rotates once every 4.25 hours. The comet Halley, one of the most famous comets in history, rotates approximately once every 2.25 days. The asteroid Itokawa, surveyed by the Japanese Hayabusa mission in 2005, rotates once every 12 hours and presents an unusual elongated shape that affects the way its rotation is perceived by observers on Earth. These small bodies, lacking the tidal damping that has stabilized the rotations of larger worlds, often retain spin rates and orientations that are direct echoes of the violent collisions of the early solar system. Each one is, in a sense, a frozen moment of ancient rotational history, preserved against the slow erosion of tidal forces because the body is too small for tidal forces to significantly affect it on timescales shorter than the age of the solar system. Some asteroids spin so fast that they are on the edge of disintegrating. The rubble pile hypothesis, which holds that many asteroids are not solid objects but loose collections of fragments held together by their own weak gravity, predicts that there should be a maximum rotation rate above which an asteroid would fly apart. Observations of the asteroid population confirm this prediction. There is a sharp upper limit on rotation rate among asteroids of moderate size, corresponding closely to the rate at which centrifugal force at the equator equals the gravitational binding force of a rubble pile. Above this limit, asteroids cannot exist because any rubble pile spinning faster would simply throw off its outer layers. This is conservation of angular momentum working in extremis, a population of small bodies whose rotations are limited by the strength of gravitational binding alone, and beyond which the universe simply cannot maintain coherent objects. The fastest rotating asteroids we know about are spinning right at the edge of this limit, and many of them are accompanied by its small satellites, chunks of rock that have been thrown off by their parent body's rotation and now orbit alongside the original asteroid as gravitationally bound companions. The solar system is, in this way, a museum of rotation. Every object in it has a story to tell about how its spin came to be, and every object, given a sufficiently sensitive observation, reveals the history of angular momentum exchanges that produced it. Stop for a moment and consider what you have just learned. A cloud of gas drifting through the galaxy 4.5 billion years ago possessed a small and almost invisible rotation. That rotation, conserved across the collapse of the cloud, became the rotation of the Sun and the orbital plane of the planets. The same rotation, expressed in the disk that surrounded the young Sun, became the orbital direction of every body in the solar system. The same rotation, inherited by the planets as they accreted from the disk, became the spin axes of those planets, modified, in some cases, by violent collisions but otherwise preserved. You are sitting on the Earth. The Earth is rotating because, 4.5 billion years ago, a cloud of gas in a quiet patch of the Milky Way happened to be turning, very slowly, around an axis that no one chose, and that no one could have predicted in advance. That ancient accidental rotation has propagated through every layer of inheritance, from cloud to disk to planet to spin to day. And it now manifests as the daily cycle of light and dark that has shaped life on Earth since its beginning. The day exists because of conservation of angular momentum. The seasons exist because of conservation of angular momentum, applied to the slightly tilted axis of the Earth's rotation, which itself is a consequence of how the Earth's spin, angular momentum, was distributed during its formation. The tides exist because of a related principle. The gravitational extraction of energy from the Earth-Moon rotation system over billions of years. Even the existence of life on Earth, to the extent that life requires regular cycles of light and dark, of warm seasons and cold seasons, of regular tidal zones in which intertidal organisms can evolve, depends on the rotation of the Earth and its companion. And that rotation is a direct consequence of the conservation law we have been discussing. You then are alive in part because of conservation of angular momentum. Your existence is downstream of a primordial spin in a cloud of gas that has long since dispersed. You are, in a real sense, made of the inheritance of that ancient rotation. Stop for a moment and consider what you have just learned. A cloud of gas drifting through the galaxy 4.5 billion years ago possessed a small and almost invisible rotation. That rotation, conserved across the collapse of the cloud, became the rotation of the Sun and the orbital plane of the planets. The same rotation, expressed in the disk that surrounded the young sun, became the orbital direction of every body in the solar system. The same rotation, inherited by the planets as they accreted from the disk, became the spin axis of those planets, modified in some cases by violent collisions but otherwise preserved. You are sitting on the Earth. The Earth is rotating because 4.5 billion years ago, a cloud of gas in a quiet patch of the Milky Way happened to be turning, very slowly, around an axis that no one chose and that no one could have predicted in advance. That ancient accidental rotation has propagated through every layer of inheritance, from cloud to disk, to planet, to spin to day. And it now manifests as the daily cycle of light and dark that has shaped life on Earth since its beginning. The day exists because of conservation of angular momentum. The seasons exist because of conservation of angular momentum applied to the slightly tilted axis of the Earth's rotation, which itself is a consequence of how the Earth's spin angular momentum was distributed during its formation. The tides exist because of a related principle: the gravitational extraction of energy from the Earth-Moon rotation system over billions of years. Even the existence of life on Earth, to the extent that life requires regular cycles of light and dark, of warm seasons and cold seasons, of regular tidal zones in which intertidal organisms can evolve, depends on the rotation of the Earth and its companion. And that rotation is a direct consequence of the conservation law we have been discussing. You, then, are alive, in part because of conservation of angular momentum. Your existence is downstream of a primordial spin in a cloud of gas that has long since dispersed. You are, in a real sense, made of the inheritance of that ancient rotation. We have descended from the universe into the solar system. Now we will go back outward, but not to the universe as a whole, not yet. Let us pause at the level of the galaxy. Because the rotation of galaxies, including our own, has revealed something about the cosmos that no one expected, and that no one yet fully understands. The Milky Way is rotating. We knew this in general terms from the early 20th century, from observations of how stars moved relative to the galactic center, from the orbital motions of star clusters and gas clouds, from the differential rotation of the disk that astronomers like Jan Oort and Bertil Lindblad worked out in the 1920s and 1930s. The rotation period at our distance from the galactic center, about 26,000 light-years out, is approximately 225 million years. The Sun completes one full orbit of the galaxy every 225 million years. The last time the Sun was at this point in its orbit, the supercontinent Pangaea was just beginning to break apart, and the dinosaurs had not yet evolved. This is what we knew. The galaxy spins, the Sun goes around. Reasonable, predictable. But there was a problem. In the 1970s, the American astronomer Vera Rubin, working at the Carnegie Institution in Washington, began making detailed measurements of the rotational velocities of stars and gas at different distances from the centers of nearby spiral galaxies. The expectation, based on Newtonian gravity and the visible distribution of mass in the galaxies, was clear. The rotational velocity should be highest near the galactic center, where the mass is concentrated, and should decrease outward, falling off in a smooth curve as the influence of the central mass weakened with distance. This is the same way the planets in our solar system orbit. Mercury moves much faster than Pluto. The further out you go, the slower the orbital motion. For galaxies, Rubin expected the same pattern. The stars in the inner regions near the bulge should be orbiting fast. The stars in the outer disk, far from the central concentration of mass, should be orbiting slowly. That is not what she found. What she found was that the rotational velocity of a galaxy, as a function of distance from the center, did not decrease in the outer regions. It stayed roughly constant. Out to the very edge of the visible disk, the stars and gas were orbiting at almost the same speed as the inner regions. The rotation curve was flat. This was, by the standards of Newtonian physics applied to the visible matter of the galaxy, impossible. Or rather, it was possible, but only if there was an enormous amount of additional mass present in the galaxy that was not visible in any wavelength of light. Mass that was distributed throughout the galaxy in a roughly spherical halo, extending well beyond the visible disk. Mass that exerted gravitational influence on the visible stars and gas, holding them in their fast orbits even at great distances from the center, but that itself emitted no detectable radiation. This was the discovery, or rather, the modern reconfirmation, of dark matter. Galaxies, Rubin's work showed, are not just collections of stars. They are stars, and gas embedded in a much larger, much more massive halo of invisible material. The stars are like the visible foam on top of a wave. The dark matter halo is the wave itself. Without the dark matter, galaxies as we know them could not exist. The visible mass of a galaxy is not enough to hold it together. Without the gravitational support of the dark halo, the outer stars and gas would simply fly away into intergalactic space. They are moving too fast to be retained by the gravity of the visible mass alone. Rubin's discovery, built on earlier theoretical work by Fritz Zwicky in the 1930s, and confirmed by independent measurements by other astronomers in the 1970s, fundamentally change how we understand the universe. We no longer live in a cosmos that is dominated by the matter we can see. We live in a cosmos in which most of the matter is invisible. About 85% of all matter in the universe is dark matter, of unknown composition, of unknown microscopic nature, but indisputably present and indisputably providing the gravitational scaffolding around which all the visible structures we observe have been built. And the rotation of galaxies is the most direct evidence of dark matter we have. The flat rotation curves are the smoking gun. Wherever astronomers point their telescopes, at spiral galaxies, at dwarf galaxies, at galaxy clusters, the rotation patterns they see require dark matter to explain. Without dark matter, the universe we observe could not have formed. The structures we live within, the Milky Way, the local group, the cosmic web, owe their existence to the gravitational influence of a substance whose particle nature remains, after 50 years of searching, unknown. We are, in a certain sense, riding on a wave of dark matter. The rotation of our galaxy, which carries the Sun on its slow orbit, is regulated not by the visible mass we can see in the sky, but by the invisible halo around us. Our motion through the galaxy, our orbital speed of 828,000 kilometers per hour, is set by the dark matter density in the halo at our distance from the galactic center. We do not know what dark matter is, but we know that without it, none of this would exist. There would be no Milky Way, there would be no Earth, there would be no you. The story of how Vera Rubin came to make this discovery is worth telling because it is one of the most quietly heroic stories in 20th century astronomy. Rubin began her career at a time when very few women were welcomed into professional astronomy. When she applied to graduate school at Princeton in the 1950s, she was told that the program did not accept women. She went instead to Cornell, then to Georgetown for her PhD, and eventually joined the Carnegie Institution. She spent decades doing patient, careful, often unglamorous work, measuring the rotational velocities of galaxies one star at a time, one spectroscopic exposure at a time, building up a catalog of observations that eventually became the foundation of modern dark matter astrophysics. When she first noticed that the rotation curves of galaxies were flat, that the outer stars were moving as fast as the inner ones, she did not immediately conclude that dark matter existed. She and her collaborator, Kent Ford, simply reported what they saw. Other astronomers, looking at her data, had to make sense of it. Some proposed alternative theories of gravity. Some suggested that the visible mass of galaxies had been miscalculated. But over time, As more and more galaxies were measured and the same flat rotation curves were observed everywhere, the dark matter explanation gained ground. It became, by the 1980s and 1990s, the consensus interpretation. By the 2000s, it had been confirmed by an independent line of evidence: the gravitational lensing of distant galaxies by intervening cluster mass, which also requires dark matter to explain. Today, dark matter is one of the central elements of modern cosmology. The standard model of cosmology, the lambda CDM model with cold dark matter and a cosmological constant, assigns about 26% of the total mass energy content of the universe to dark matter. Ordinary matter, the stuff we can see, accounts for only about 5%. The rest, about 68%, is dark energy, an even more mysterious component that drives the accelerating expansion of the universe. Vera Rubin died in 2016 without ever seeing dark matter directly detected in a laboratory. The search continues. Underground detectors, deep beneath mountains in Italy and South Dakota and China, run for years at a time, hoping to catch a single dark matter particle interacting with their atomic nuclei. So far, they have found nothing. The nature of dark matter remains, as of today, completely unknown at the level of fundamental physics. But its gravitational influence is everywhere, in every galaxy, in every cluster, in every measurement of large-scale structure. The rotation of the Milky Way, the orbital motion of the Sun, the slow precession of the local group. All of these are governed in detail by the dark matter halos in which our visible structures are embedded. We are riding on something we cannot see. The rotations we observe in the cosmos are, in a deep sense, rotations of dark matter. The visible stars are merely tracers, painting on the surface of a much larger and much more massive object, whose true nature we have not yet identified. How does a galaxy come to be rotating at all? Where does the angular momentum of a galaxy come from? This is one of the questions that cosmologists have spent decades trying to answer in detail. The general framework is reasonably well understood. In the early universe, dark matter over densities, slight regions of higher density in the otherwise smooth distribution of matter that filled the cosmos, began to attract material gravitationally. As they grew, they exerted tidal torques on each other. When two neighboring overdensities were not perfectly spherical, and they almost never were, the gravitational pull of one on the other did not act through the center, but slightly off-center. This off-center pull imparted a small rotational impulse to each overdensity in opposite directions. This is called tidal torque theory, and it is the standard explanation for the origin of galactic angular momentum. According to the theory, every galaxy in the universe acquired its initial spin from tidal interactions with its neighbors during the early stages of structure formation in the first few 100 million years after the Big Bang. The rotation of each galaxy is, in essence, a record of those primordial torques, a fossil of the gravitational pulls that nearby overdensities exerted on each other before the galaxies themselves had even fully condensed. The theory works broadly. Simulations of galaxy formation that include the effects of tidal torques produce galaxies whose rotational properties match observations reasonably well. The total angular momentum of a typical galaxy, the way that angular momentum is distributed between the disk and the halo, the relationship between galaxy mass and rotation rate. All of these have explanations in some degree of detail within the framework of tidal torque theory. But there are subtleties, there are puzzles, there are observations that do not fit cleanly into the theory. One of them is the JWST asymmetry we discussed at the beginning of this film. If galactic rotations were entirely random, set by chance encounters between primordial overdensities in an isotropic universe, then in any large sample, we should see equal numbers of clockwise and counterclockwise spinners. The fact that JWST data shows a 60-40 split is, on the face of it, a violation of this expectation. Either there is some mundane explanation, measurement bias, sample limitations, observational selection effects, or there is something deeper going on, something that introduces a preferred direction into the universe at the largest scales, something that biased the original tidal torques in the early cosmos toward one direction over the other. We do not know which, but the question is now open, in a way that it had not been open for many decades, and it leads us naturally to the most extreme rotation in the universe, to the rotation of the singularity, the rotation of the spinning black hole. A spinning black hole is unlike anything else in the universe. Most spinning objects, stars, planets, galaxies, rotate as bodies of matter, with their substance physically moving in circles around a central axis. A spinning black hole does not. A black hole is not a body of matter in the conventional sense. It is a region of space-time, a geometry, a place where the curvature of the universe has become so extreme that no path through it can escape outward to the rest of the cosmos. The interior of a black hole, in classical general relativity, contains a singularity, a point, or, in the case of rotating black holes, a ring, where the curvature of space-time becomes infinite. But the rotation of the black hole is not exactly the rotation of this singularity. It is rather a property of the space-time geometry as a whole. The black hole's angular momentum is encoded in the way that space and time are bent around it. And one of the consequences of this geometric rotation is an effect with no analog in everyday physics. It is called frame dragging. Frame dragging is the prediction, made by Einstein's general theory of relativity, that a rotating massive body literally drags the fabric of space-time around with it. The space surrounding the rotating mass does not stay still. It is twisted slightly in the direction of rotation. Inertial frames, the reference frames in which Newton's laws of motion would hold for a freely falling observer, are pulled along by the rotating mass, and observers nearby find themselves rotating with the space-time even if they are not under the influence of any conventional force. For an ordinary rotating body, like the Earth, frame dragging is incredibly weak. The Earth drags space-time around itself by a few hundredths of an arc-second per year. Detecting it requires a satellite-based experiment of breathtaking precision. The Gravity Probe B mission, launched by NASA in 2004, was designed specifically to measure this tiny effect, and after years of operation, it confirmed that the Earth does indeed twist the local space-time, in agreement with general relativity. But for a spinning black hole, frame dragging is overwhelming. Near the event horizon of a rapidly rotating black hole, the rotation of space-time itself becomes so strong that no observer, no matter how powerful their rocket, can remain stationary with respect to distant stars. They are forced to rotate. The space around them is being pulled at speeds that approach the speed of light, and they are being pulled along with it. This region, the region in which it is geometrically impossible to stand still, is called the ergosphere. Inside the ergosphere of a spinning black hole, the laws of physics begin to behave strangely. Energy can be extracted from the rotation of the black hole through a process called the Penrose mechanism, named after the British mathematician Roger Penrose. By dropping an object into the ergosphere and arranging for it to split into two pieces in just the right way, one piece can fall into the event horizon while the other piece escapes back to infinity with more energy than the original object had. The extra energy comes, ultimately, from the rotation of the black hole, which decreases slightly each time the process is performed. This is not a thought experiment. It is a real physical effect, and it has been observed in nature in indirect form. The relativistic jets that emanate from the centers of active galaxies, including the giant radio galaxy Porphyrion that we have discussed in other films, are believed to be powered, in part, by the Penrose mechanism operating on supermassive black holes. The energy of those jets, the staggering luminosity of those active galactic nuclei, comes from the slow extraction of rotational energy from spinning black holes through the twisting of space-time in their ergospheres. The black holes are de-spinning. Slowly, over hundreds of millions of years, they are giving up their angular momentum to the universe through the production of jets and radiation. The angular momentum, conserved as it must be, is being transferred outward from the black hole to the surrounding intergalactic medium. The black hole spins more slowly. The medium gets a tiny bit of energy and motion. Order is preserved, but the spin itself, while it lasts, is the most extreme form of rotation we know. Before we go further into the geometry of black hole rotation, I want to take a brief detour through the most observable form of extreme rotation in the universe: pulsars. A pulsar is a rotating neutron star whose magnetic axis is misaligned with its rotation axis. As the pulsar spins, beams of radiation from its magnetic poles sweep across space like the beams of a lighthouse, when one of those beams happens to be aimed at Earth, and the geometry is right for us to see it as the pulsar rotates. We observe a series of regular pulses, one each time the beam crosses our line of sight. Hence the name pulsar, from pulsating radio source, even though the source is not actually pulsating, but rather rotating. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell, working at Cambridge with her supervisor, Anthony Hewish. Bell was analyzing data from a radio telescope when she noticed a strange, regular signal coming from a fixed point in the sky. The signal had a period of 1.337 seconds, a precision so remarkable that the team initially considered, half seriously, the possibility that it was an artificial signal from an extraterrestrial civilization. They labeled the source LGM1 for Little Green Men. It turned out, of course, not to be a signal from another civilization. It was a rotating neutron star, the collapsed core of a star that had ended its life in a supernova explosion. The neutron star itself was about 20 kilometers across, weighed about 1.5 times the mass of the Sun, and was rotating once every 1.337 seconds. The intense magnetic field around the star, magnetic fields trillions of times stronger than the Earth's, was channeling streams of charged particles into beams that swept past the Earth as the star rotated. Within a few years, dozens of pulsars had been discovered, then hundreds. Today, the catalog includes thousands. They range from young, fast-spinning pulsars whose periods are measured in milliseconds, some of them rotating more than 700 times per second, to older, slower pulsars with periods of several seconds. Every one of them is a tiny example of conservation of angular momentum applied to its absolute logical extreme. A pulsar's surface is moving, at the equator, at substantial fractions of the speed of light. The fastest known pulsars have equatorial surface velocities of about 10% of the speed of light. Their bodies are held together against the centrifugal tear only by the extraordinary strength of degenerate neutron matter. Matter so compressed that the protons and electrons of normal atoms have merged into neutrons, and the neutrons themselves are packed against each other with quantum mechanical resistance to further compression. The Crab pulsar, formed from a supernova that Chinese astronomers observed in 1054 CE, rotates 30 times per second. Its young age, less than 1,000 years, means it has not yet had time to slow down significantly through magnetic dipole radiation. The Crab is, in a sense, a fossil moment of an ancient stellar collapse, preserved across nearly a millennium, and still spinning at the rate it acquired in those first chaotic moments after its parent star died. When pulsars are observed over years and decades, their pulse periods can be measured with extraordinary precision. The most stable pulsars are, in some respects, more accurate clocks than the best atomic timekeepers humans have built. They can be timed to within nanoseconds over periods of months, and these timing measurements have been used to detect, indirectly, the presence of planets around pulsars. the first exoplanets ever discovered, found in 1992 around the pulsar PSRB 1257+12. By observing the tiny variations in pulse arrival times caused by the gravitational tug of orbiting bodies, pulsars have also been used as detectors of gravitational waves. Pulsar timing arrays, which monitor dozens of stable pulsars across the sky, can detect the passage of long wavelength gravitational waves through our galaxy by observing correlated variations in the arrival times of pulses from different directions. In 2023, the first evidence of a stochastic gravitational wave background, likely produced by the slow in spirals of supermassive black hole binaries throughout cosmic history, was reported using exactly this technique. The fact that we can do all of this, that we can use the rotations of dead stars as cosmic timekeepers, is a remarkable testament to the precision and durability of the rotations the universe has produced. Every pulsar is a clock. Every clock is a record of conservation of angular momentum. Every record reaches back, ultimately, to the original rotation of the cloud from which the pulsar's progenitor star was born, billions of years ago, in some long-vanished part of the Milky Way. In 2019, the Event Horizon Telescope released the first ever direct image of a black hole. The image showed the supermassive black hole at the center of the M87 galaxy, an enormous elliptical galaxy 55 million light-years from Earth. The black hole, with a mass of about 6.5 billion suns, was visible as a dark central region, the shadow of the event horizon, surrounded by a ring of luminous matter, the accretion disk seen from a particular geometric perspective. The image was extraordinary. It was the first direct visual confirmation of the existence of a black hole. It was the first time human eyes had seen, in any meaningful sense, the boundary at which space-time itself becomes inescapable. And it was a remarkable feat of engineering, the event horizon. Telescope was not a single telescope, but a global network of radio dishes, working together as a single virtual telescope the size of the Earth itself, with enough resolving power to detect a structure the size of an orange on the surface of the moon. But for our purposes here, the most important feature of the M87 image was its asymmetry. The ring of light around the black hole was not uniform. One side of the ring was visibly brighter than the other, and the brighter side was the side where the matter of the accretion disk was moving toward the Earth, while the dimmer side was the side where the matter was moving away. This was relativistic Doppler beaming, and it was direct evidence that the accretion disk around the M87 black hole was rotating. The matter on the approaching side appeared brighter because of relativistic effects that boost the apparent luminosity of fast-moving sources moving toward an observer. The matter on the receding side appeared dimmer for the corresponding reason. The pattern of brightness across the ring was a fingerprint of rotation, and from the asymmetry, the Event Horizon Telescope team was able to estimate the spin of the black hole itself. M87's central black hole is rotating, like most supermassive black holes, at a substantial fraction of its maximum possible rate. The ergosphere around it is dragging space-time in the direction of rotation, accelerating matter, helping to launch the relativistic jet that the M87 nucleus is famous for. In 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Sagittarius A star is a much smaller black hole than M87, about 4 million solar masses, less than 1,000th the mass of M87. But it is also much closer, only about 26,000 light-years away. The combination meant that, despite Sagittarius A star's smaller absolute size, its angular size on the sky was comparable to that of M87. The image of Sagittarius A star, like the image of M87, showed a dark central shadow surrounded by a luminous ring, and like M87, the ring showed asymmetric brightness consistent with rotation. The black hole at the center of our galaxy is spinning. The exact spin parameter is still being refined as more observations come in, but it appears to be a moderately fast rotator, with a spin rate that is a substantial fraction of the maximum allowed by the Kerr metric. Even our quiet galactic center, which is not currently producing dramatic relativistic jets, and which is in a relatively quiescent phase of its life cycle, has a black hole at its heart that is rotating in the most extreme way the universe permits. This is perhaps the most disturbing realization of all. The black hole at the center of the Milky Way, the gravitational anchor that helps hold our galaxy together, that organizes the orbits of millions of stars in the inner regions of the bulge, that has been observed for years through the orbits of stars that approach its event horizon and survive, is itself spinning at a rate that twists the space-time of the intergalactic core. The frame dragging it produces is too small to affect us at our distance from the galactic center. But it is real, and it is happening, and it has been happening for as long as the black hole has existed. You are spinning. The Earth is spinning. The sun is spinning. The galaxy is spinning. The black hole at the center of the galaxy is spinning, dragging space-time with it as it does so. And every level of this rotation, every layer of this nested motion, is connected by conservation laws that have been operating since before the Earth existed. The mathematical description of a rotating black hole is given by something called the Kerr metric, named after the New Zealand mathematician Roy Kerr, who derived it in 1963. The Kerr metric is the exact solution to Einstein's field equations for a rotating, uncharged black hole, and it remains one of the most important and most studied solutions in all of general relativity. The Kerr metric tells us, with mathematical precision, what the space-time around a spinning black hole looks like. It tells us the shape of the ergosphere. It tells us the location of the event horizon, which, for a rotating black hole, is not quite the same as for a non-rotating one. It tells us about the existence of the inner horizon, a strange surface, inside the black hole at which the geometry of space-time undergoes another kind of transition. And it tells us about the ring singularity at the center, a curious object that, mathematically, is a one-dimensional ring of infinite curvature rather than a zero-dimensional point. It also reveals one of the most disturbing facts about black hole physics. There is a maximum spin rate that a black hole is allowed to have. The maximum spin is called the extremal Kerr limit, and it corresponds to a configuration in which the angular momentum of the black hole has reached the largest value compatible with the existence of an event horizon at all. If a black hole spun faster than this, the event horizon would mathematically disappear, and the singularity at the center would be exposed to the outside universe, a state called a naked singularity, which is generally considered impossible by most theorists. We do not believe that any naked singularities exist. The cosmic censorship hypothesis, proposed by Roger Penrose, states that all singularities in our universe are hidden behind event horizons, that the laws of physics conspire to prevent us from ever seeing one directly. Whether this is rigorously true remains a subject of debate, but no observational evidence has ever suggested otherwise. What this means, practically, is that a black hole's spin can be arbitrarily fast, but it cannot be infinitely fast. There is a hard upper bound set by the geometry of space-time itself, and many of the observed supermassive black holes in the universe are believed to be spinning very close to this maximum. The black hole at the center of the Milky Way, Sagittarius A star, has a spin parameter that has been estimated by various methods to be a substantial fraction of the maximum allowed value. The supermassive black hole at the center of the M87 galaxy, the first black hole ever directly imaged by the Event Horizon Telescope in 2019, is similarly fast spinning. Many active galactic nuclei, whose accretion physics has been carefully studied, appear to have black holes near the extremal limit. These objects, then, are not just rotating. They are spinning at the maximum rate the universe permits. They are the absolute extremes of cosmic rotation. the limit cases beyond which the geometry of reality itself would have to break down. And every one of those black holes, in obedience to the same conservation law that governs the figure skater and the collapsing cloud, is slowly losing its rotation through the production of jets and the slow leakage of angular momentum into the surrounding cosmos. The spin of the universe, in all its forms, is being transferred. Always transferred, conserved across every interaction, but never permanent in any one location. We have been climbing through the rotations of the universe, from the daily turn of the Earth up to the relativistic frame dragging of supermassive black holes. Now we will plunge in the other direction, down through the molecular, the atomic, the subatomic, into the quantum realm where the very concept of rotation begins to break down, and where a different kind of spin, strange, unintuitive, and yet absolutely real, takes over. Hold on. The descent we are about to make is unlike any other. There is something every electron in your body is doing right now that no one in the history of physics has ever been able to fully explain. It is spinning, not in the way a top spins, not in the way a planet spins. Electrons are not, as far as anyone has been able to determine, physically rotating objects. They have no measurable size, no detectable internal structure, no surface that could be moving in a circle around an internal axis. By every test we have been able to devise, electrons are point-like particles with no extension and no substructure, and yet they have a property called spin, a property with units of angular momentum, a property that interacts with magnetic fields in exactly the way that a tiny rotating charged sphere would interact, a property that contributes to the total angular momentum of the atom in which the electron resides, and that obeys conservation of angular momentum just as the rotation of a galaxy does. How can a point-like particle have angular momentum? This question, which has tormented physicists since the discovery of electron spin in 1925, has no satisfactory classical answer. The honest response is that electron spin is not, despite its name, the same kind of thing as macroscopic rotation. It is a quantum mechanical property, an intrinsic property of the particle, like its charge or its mass, that happens to behave in many ways like rotation, but that cannot be reduced to any underlying spinning motion of substructure. Spin, in this sense, is one of the great mysteries of the standard model of particle physics. It is a property we have to accept as fundamental, alongside mass and charge, even though we have no satisfying picture of what it really is. Every electron has spin. Every quark has spin. Every neutrino has spin. The photons of light streaming from your screen into your eyes carry spin. The gluons that hold the protons in the nuclei of your atoms together carry spin. Spin is everywhere in the quantum realm, and it cannot be turned off. It is, in some sense, the deepest level at which the universe rotates. The discovery of electron spin came from one of the most elegant experiments in the history of physics. In 1922, two German physicists, Otto Stern and Walter Gerlach, performed an experiment that, on its face, seemed simple. They sent a beam of silver atoms through a strong, non-uniform magnetic field, and they watched where the atoms ended up on a detector screen on the other side. They expected, based on classical physics, that the atoms would spread out continuously across the screen. The classical prediction was that the magnetic moments of the atoms, which arise from the motion of the electrons within the atoms, would have a continuous range of orientations relative to the magnetic field, and that the deflections of the atoms would correspondingly be continuous. What they found was that the atoms did not spread out continuously. They split into exactly two beams. Half of the atoms went up. The other half went down, and there was nothing in between. This was, by the standards of classical physics, impossible. The angular momentum of an atom should not be quantized into only two possible values along any given axis. There was no way to explain the result without invoking some new property of the electron, a property that took on only two values, up or down, with no intermediate states allowed. This property, 3 years later, was identified as electron spin. The two values were eventually labeled spin up and spin down, and the units in which they are measured, the famous reduced Planck's constant divided by 2, became one of the foundational quantities of quantum mechanics. What the Stern-Gerlach experiment showed, and what every subsequent experiment in atomic and subatomic physics has confirmed, is that the universe at the smallest scales is granular. Angular momentum is not continuous. It comes in discrete packets, multiples of a fundamental unit, with no values in between allowed. An electron cannot have a spin angular momentum of 0. It cannot have a value between up and down. It must be one or the other, and only one or the other. This quantization of angular momentum is one of the defining features of quantum mechanics. It applies to all forms of angular momentum at the quantum level: orbital angular momentum, the angular momentum of an electron orbiting a nucleus, as well as spin angular momentum. Both are quantized, both come in discrete units, both reveal the deep granularity of the cosmos at the quantum scale. And this granularity has consequences that ripple all the way up to the macroscopic world. The reason atoms have stable structures is, in part, a consequence of the quantization of angular momentum. The reason electrons and atoms occupy discrete energy levels, and not a continuous range of energies, is a consequence of the same quantization. The reason chemistry exists at all, with its orderly periodic table and its predictable bonding patterns, is a consequence of the fact that electrons cannot have arbitrary spin or orbital angular momentum, but must take on values from a discrete set. The Pauli exclusion principle, which states that no two electrons in an atom can have the same set of quantum numbers, depends critically on the existence of electron spin. Because electrons have two possible spin states, two electrons can occupy the same orbital, but no more than two. This is why atoms have the particular shell structure they do. This is why the periodic table has the particular shape it has. This is why the elements have the particular chemical properties they have. Spin, then, is not just a curious feature of subatomic particles. It is one of the foundations of chemistry, of biology, of material science, of every aspect of the physical world that depends on the structure of atoms and molecules. The fact that electrons have spin is, in a deep sense, the reason there is anything as complex as a living organism in the universe at all. There is a deeper layer still. In 1928, a young British physicist named Paul Dirac wrote down an equation that combined quantum mechanics with special relativity. Dirac was trying to construct a wave equation for the electron that would be consistent with Einstein's theory of relativity, in addition to being consistent with the quantum principles that had been developed in the previous several years. The equation he ended up with, the Dirac equation, was a mathematically beautiful object, and it had a remarkable consequence. It predicted electron spin. Dirac had not put spin into the equation by hand. He had not assumed it. He had simply asked what equation would describe an electron in a way that was consistent with both quantum mechanics and relativity. And the equation that emerged automatically required the electron to have a spin of 1/2. The mathematical structure of relativistic quantum theory demanded it. This was an extraordinary result. It meant that electron spin was not just an empirical fact about the universe, something that experiments had revealed and theorists had to incorporate. It was a logical consequence of the deep structure of physics. Once you accept relativity and quantum mechanics together, you cannot avoid spin. It is built into the mathematical fabric of reality. The spin of the electron, then, is not arbitrary. It is not contingent. It is the unavoidable consequence of the laws that govern the universe at the most fundamental level. Every electron has spin 1/2 because the universe is relativistic and quantum mechanical. It could not be otherwise. This insight extends to other particles as well. Every fundamental particle in the Standard Model has a spin that is either 0, 1/2, 1, or 2. The values are not arbitrary. They are determined by the symmetries of the underlying physics. Particles with half-integer spin are called fermions. They obey the Pauli exclusion principle. They make up matter, quarks, leptons, the building blocks of atoms. Particles with integer spin are called bosons. They do not obey the Pauli exclusion principle. They mediate forces. The photon, the gluon, the W and Z bosons of the weak force, the hypothesized graviton. The division between fermions and bosons, between matter and force, is at root a division of spin. Without spin, there would be no distinction between matter and force. Without the Pauli exclusion principle, which depends on spin, atoms would collapse into a single quantum state. Without the spin properties of force-carrying bosons, the fundamental forces of nature could not propagate the way they do. Without spin, in short, the universe as we know it could not exist. Spin is not a peripheral feature of physics. It is structural, it is foundational, it is the invisible architecture upon which the visible cosmos has been constructed. And it remains, after a century of careful study, deeply mysterious. We do not know why spin exists in the form it does. We do not know why fermions have half-integer spin and bosons have integer spin. We have descriptions, but not explanations. We have mathematics, but not understanding. The universe at its smallest scales is rotating. But what it is that rotates, and what the rotation actually is, remains an open question. There is something practical about quantum spin that is worth pausing to consider, because it shows up in everyday life in ways most people never realize. If you have ever had a magnetic resonance imaging scan, an MRI, at a hospital, you have benefited directly from the spin of the protons in your body. An MRI machine works by exploiting the spin of hydrogen nuclei. Every hydrogen atom contains a single proton in its nucleus, and every proton has a spin of 1/2. Inside the strong magnetic field of the MRI machine, those proton spins align themselves with the field, most pointing in one direction, a slight excess pointing the other way. The machine then sends in a precisely tuned radio frequency pulse that flips the spins. As the spins relax back to their original alignment, they emit detectable radio waves whose properties depend on the local environment of each proton. By analyzing those emitted radio waves, the machine can construct a three-dimensional image of the inside of your body. Different tissues, muscle, fat, brain matter, blood, contain different densities of hydrogen and have different relaxation properties, so they show up with different brightness in the resulting image. Tumors, lesions, soft tissue injuries, all of them are visible to MRI in ways they are not visible to X-rays or ultrasound. The technology depends at every step on the quantum spin of the proton. Without spin, MRI would not exist. Without spin, modern medicine would be missing one of its most important diagnostic tools. The same is true of nuclear magnetic resonance spectroscopy, used by chemists to determine the structure of molecules, and electron spin resonance, used to study free radicals and unpaired electrons in materials. Both techniques exploit the quantum spin of subatomic particles to extract information that no classical measurement could reveal. The fact that electrons and protons spin in their strange quantum way is the foundation of an entire branch of analytical science. When you walk through a hospital and see the MRI suite, you are seeing a machine that is, at the most fundamental level, a measurement of quantum spin, and the spin it measures, the intrinsic angular momentum of every hydrogen nucleus in your body, is a property whose origin we cannot yet fully explain, even though we have learned to manipulate it with extraordinary precision. The spin of the proton, by the way, is itself a continuing puzzle in particle physics. We know that the proton has a spin of 1/2, but we do not fully understand where that spin comes from. The proton is composed of 3 quarks held together by gluons, and naively one might expect that the spin of the proton would simply be the sum of the spins of its 3 constituent quarks, but it is not. When physicists in the 1980s used polarized scattering experiments to measure the contribution of quark spins to the total spin of the proton, they found a stunning result. The quarks contribute only about 30% of the proton's total spin. The remaining 70%, the majority of the spin, comes from somewhere else. Where exactly is still a subject of active research. Some of it appears to come from the spin of the gluons that mediate the strong force inside the proton. Some of it comes from the orbital angular momentum of the quarks and gluons as they move within the proton. The detailed accounting is still being worked out by experiments at facilities like the upcoming Electron-Ion Collider, scheduled to begin operation later this decade at Brookhaven National Laboratory. The proton spin crisis, as it was dramatically called in the 1990s, is one of the deepest puzzles in modern particle physics. We have a particle whose spin we know perfectly, whose constituents we have identified, and yet we cannot fully account for where its spin comes from. It is as if the universe is hiding angular momentum from us, distributing it in subtle ways across the internal structure of subatomic particles, in patterns we can only partially trace. This too is rotation. And like every other rotation we have discussed, its origins go back to the deepest layers of physics, to the quantum chromodynamics of the strong force, to the gauge symmetries of the Standard Model, to the foundational laws that govern the substance of reality at scales no microscope will ever resolve. We have come full circle. We started with a count of 263 galaxies in a JWST image, an asymmetry in their rotations that did not match the expectations of an isotropic cosmos. We descended through the scales of structure, galaxies, solar systems, planets, atoms, particles. We found that at every level of the universe, things are turning. We found that conservation of angular momentum, applied to a universe that was never perfectly still, has produced an amplified rotation across 13.8 billion years of cosmic history. We found that even at the quantum level, where macroscopic rotation no longer applies, the universe still has spin built into its fundamental particles, an intrinsic angular momentum that cannot be removed. Now we return to the largest scale, to the question of whether the universe itself is rotating. If the JWST asymmetry holds, if larger surveys, with more galaxies, with different telescopes, in different parts of the sky, confirm that there is a real preferred direction of galactic rotation in the cosmos, then the Standard Model of cosmology is in trouble. The Standard Model assumes isotropy. It assumes no preferred direction. The presence of a cosmic axis, an orientation built into the universe at the largest scales, would force a revision of the framework that has dominated cosmology for 30 years. What would replace it? The leading candidate at the moment is some form of rotating universe model. There are several mathematical frameworks for such cosmologies, going back to the work of the mathematician Kurt Gödel, who, in 1949, derived an exact solution to Einstein's field equations corresponding to a universe with global rotation. Gödel's universe was strange in many ways. It allowed for closed time-like curves, mathematical paths through space-time that loop back to their own past, raising deep questions about the consistency of physics in such a cosmos. But the central idea that a universe could, mathematically, be rotating as a whole was established. The equations permit it. More recent models, developed in the past several decades, have explored different versions of cosmic rotation. Some posit a slow, almost imperceptible global spin that would have negligible local effects but would imprint a small preferred direction on the large-scale structure of the cosmos. Others consider rotational asymmetries arising from the early universe, primordial gravitational waves, anisotropic inflation, or initial conditions that broke perfect isotropy from the start. And then there is black hole cosmology. This is the most radical of the proposals. It says that our entire universe is the interior of a black hole, that what we perceive as the expanding cosmos, the galaxies receding from us in every direction, the cosmic microwave background filling all of space with its faint warmth, is the inside view of a singularity that, from the perspective of some larger universe, appears as an ordinary stellar mass or supermassive black hole. The edge of our universe, the cosmological horizon beyond which we cannot see, corresponds in this framework to the event horizon of the parent black hole. If our universe is the inside of a rotating black hole, then it would inherit the angular momentum of that parent. The spin of the original black hole, projected through the singular boundary that gave birth to our cosmos, would manifest as a global rotation of our universe. The fact that everything inside our cosmos appears to spin, the fact that galaxies have a preferred direction, that the cosmic microwave background shows hints of large-scale anomalies, that the deep universe seems to have an axis, would all be downstream of the same primordial source. We would spin because our parent spins. The galaxies would have a preferred axis because the black hole that birthed our cosmos had a preferred axis. The very fact that everything in the universe rotates would not be a coincidence, not a consequence of the conservation of angular momentum starting from random initial conditions, but a direct inheritance from a previous reality. This is, at the moment, speculation. The black hole cosmology hypothesis is not part of the mainstream of theoretical physics. It is treated by most cosmologists as an interesting mathematical possibility, rather than as a serious candidate for the structure of reality. The evidence for it is suggestive but not conclusive. The JWST asymmetry might evaporate when larger samples are examined. The hypothesis itself faces deep theoretical challenges, including the question of how a universe can be born from a singularity in any physically coherent way. But it is the kind of idea that, if it turned out to be true, would resolve the deepest question in cosmology in a single stroke. It would explain why the universe is full of rotation rather than empty of it. It would explain why every collapsing structure ends up spinning. It would explain why the JWST data shows what it shows. It would tell us that the universe we inhabit is not the only one, that before the Big Bang there was something else, that somewhere outside our cosmological horizon, in a vast and unreachable larger reality, the parent black hole that gave us birth is still there, still rotating, still feeding our universe with the angular momentum that has, over 13.8 billion years, become every spinning galaxy and every spinning star and every spinning planet and every spinning particle inside us. Stop. Take a moment. The question we asked at the beginning of this film was a simple one. Why does everything in the universe spin? The answers we have found are many. Conservation of angular momentum applied to collapsing systems produces rotating end states from initially rotating clouds. Tidal torques in the early universe imparted angular momentum to forming galaxies. Quantum mechanics, in combination with relativity, requires that fundamental particles carry intrinsic spin. Frame dragging, predicted by general relativity, twists the space-time around rotating massive bodies. Rotation cascades down through every level of structure formation, from the supercluster to the subatomic, in obedience to the same conservation laws. But the deeper question, the question of where the original angular momentum came from, of why the universe is full of rotation and not empty of it, of why anything spins instead of nothing spinning, has no settled answer. The JWST data points toward a universe with a preferred direction. The black hole cosmology hypothesis offers a possible explanation for that direction, but neither is yet established as scientific fact. We are at the edge of a deep, long, ongoing investigation. The next decade, the next generation of telescopes, including the Square Kilometer Array, the Vera Rubin Observatory, the next Webb-class space telescopes that have not yet been built, will likely give us the answers we cannot give today. What we can say today is this: you are sitting in a universe in which nothing is at rest. From the largest scales of the cosmic web down to the smallest scales of quantum field theory, the substance of reality is spinning. The Earth turns beneath you. The sun turns at the heart of the solar system. The galaxy turns in its slow and ancient way. The local group and the supercluster turn more slowly still. The fundamental particles in your body have intrinsic angular momentum that cannot be removed. You are, in every meaningful sense of the word, in motion. You always have been. You always will be. The universe is a place of rotation. I want to leave you with one final thought. The figure skater, with whom we began this exploration of the conservation law that governs all rotation, is a small example of a much larger principle. The skater's spin is conserved as she pulls in her arms. She goes from a slow turn to a near blur. But that is just one small expression of a law that governs everything from her body to the universe. You can think of the cosmos as a kind of cosmic pirouette, a vast billion-year skater gathering herself in, pulling her mass, her stars, her galaxies, her clouds of gas, closer and closer to the various axes of rotation that have been established at every scale of structure. And at every scale, every level, every nested rotation inside another rotation, the universe is spinning faster as it concentrates. The cosmic dance is accelerating. It will continue to accelerate, in some sense, forever. The local rotations may slow, through tidal interactions, through magnetic braking, through the slow leakage of angular momentum to the surrounding medium. But at the level of the universe as a whole, the angular momentum is not going anywhere. It is conserved. It is permanent. It will be there, in some form, until the very last star burns out, and the very last black hole evaporates, and the cosmos enters its final, dark, dispersed phase trillions and trillions of years from now. Even then, when the stars are dead, when the galaxies have fallen silent, when the universe is a vast and freezing emptiness, even then, the leftover photons of the cosmic background will still carry angular momentum. The leftover particles, drifting in the dark, will still have spin. The fundamental quantum properties of the cosmos will still encode rotation somehow, somewhere, in the structure of whatever remains. The universe will not stop spinning, not ever. Not until the laws of physics themselves have been replaced by something we cannot now imagine. We are, all of us, riders on the cosmic wheel, briefly conscious, briefly aware, briefly capable of asking why the wheel turns. And when we look up at a clear night sky and we see the stars in their ancient slow motion across the dome of the heavens, that motion, the apparent rotation of the celestial sphere, is not just an illusion of our own daily turn. It is an echo of the same principle that turns the figure skater on the ice, that turns the galaxy in its ancient orbit, that turns the electron in its quantum dance. It is the same rotation. It is the same law. It is, in every sense that matters, the same motion. The universe spins. You are part of the spinning. You always have been. When Leor Shamir counted his 263 galaxies, he was looking for something. He may have found it, or he may not have. Future telescopes will tell us. Future surveys, future cosmological measurements, future generations of theorists working on the problem of cosmic isotropy will tell us whether the asymmetry was real or whether it was an artifact of measurement. But the question he was asking, The question that all of cosmology, in some sense, has been asking since the beginning, was not really about galaxies. It was about us, about where we came from, about what kind of cosmos we live in, about whether the rotation we feel in the daily turn of the Earth and in the slow procession of the stars overhead is just a local phenomenon, or whether it is a window into a much deeper truth. If the universe spins, it spins for a reason. That reason may be older than the Big Bang. It may be inherited from a place we can never reach. It may be the slow, distant whisper of a parent black hole, holding our entire reality inside it, like a child held in a slow turn. We do not know. We may not know for a very long time, but the question is open. The data is suggestive. The galaxies, when we count them carefully, appear to have a preferred direction. And that direction, if it is real, is telling us something profound about the cosmos in which we exist. The universe, perhaps, is rotating. We have been, perhaps, rotating with it for 13.8 billion years. And every time the Earth turns beneath you, every time the sun rises and sets in obedience to the ancient spin imparted to the solar nebula 4.5 billion years ago, every time you feel the dizziness of a fast turn or the steadiness of standing still, you are, in some small way, participating in a motion that began before there was anyone to feel it. You are spinning. The universe is spinning, and we are only just beginning to learn why.